This poster is about a method we are developing that combines deep learning and compressed sensing for high dynamic range image acquisition. High dynamic range imaging is an important problem in imaging and photography. The range of luminances in a real-world scene that we can view with our own eyes is significantly larger than the 8 to 10 bits of current image sensors. For example, in this image, the exposure was set to properly capture the foreground. Then, as a result of the limited dynamic range of the sensor, the sky is completely saturated. In the image on the right, if we set the exposure to capture the sky, the foreground becomes too dark. We want to be able to capture all of the dynamic range of a scene in a single shot. Here on the left, you can see a tone-mapped HDR image. On the right, you can see the dynamic range as stops color-coded. There are many approaches to acquiring an HDR image. Multi-bracketing involves merging multiple images taken at different exposures. This can be done with ordinary cameras, but doesn't work well for dynamic scenes. Multi-sensor solutions work well, but need special equipment and require precise calibration. The ideal solution involves reconstructing an HDR image from a single shot. Many state-of-the-art single-shot techniques either use reverse tone mapping to extend the dynamic range, or they capture a coded image and reconstruct an HDR image from it. This reconstruction of a coded image has been done using compressed sensing, and we aim to build off of these methods. Compressed sensing is a technique that reconstructs an undersampled signal. The input is the captured image Y and the measurement mask omega, and the goal is to reconstruct the signal alpha from limited measurements. While compressed sensing has led to impressive results and worked well for reconstructing an HDR image from a coded low dynamic range image, it has limitations. The patch-based nature of a reconstruction leads to artifacts and a loss of global structures. It is computationally expensive and slow. There are limitations in the reconstruction quality, since simple linear combinations of image patches lack complexity. Advances such as convolutional sparse coding have improved on some of these limitations, especially by doing a global reconstruction, but a lot of room for improvement still remains. Our approach combines deep learning and compressed sensing for single-shot HDR image capture. As input, we take a low dynamic range image with coded exposures that avoid largely saturated or underexposed areas. An example of what this would look like is on the left. Then, we use a deep compressed sensing approach to obtain a final image. An example of a tone-mapped reconstruction of what our final method would produce is on the right. The deep learning-based reconstruction I will describe addresses many limitations of compressed sensing. It's faster, and by using a neural network that composes multiple layers with nonlinearities to generate the reconstruction, our model has a complexity that compressed sensing cannot match. Overall, deep learning does away with the hard constraints of traditional optimization that are difficult to fulfill in practice. Our reconstruction approach is based off an algorithm in the 2017 paper, Compressed Sensing Using Generative Models, which solves the problem of taking a measured signal and reconstructing the original signal. However, for reconstruction, the algorithm uses a deep generative model. The reconstruction works by first training a GAN so the generator can output images like our desired HDR image when given random noise. Then, we recover an image from measurements using the generator by optimizing the latent vector Z. We train a GAN, which has a generator and a discriminator which work together with a minimax optimization so that the generator can create realistic-looking fake images. The generator takes as input a latent vector Z, which is random noise during training, and outputs a fake image. The discriminator takes as input real training examples and fake images from the generator and classifies its input as real or fake. Once it is trained, the generator can produce images that match those in the training set. For the actual reconstruction, only the trained generator is used. The quality of the generated image is very important for getting good reconstructions, so the training of the GAN is a critical step. We obtain the reconstruction of an image by optimizing the latent vector Z that is input to the generator. The loss for Z is computed by taking the sum squared error between the measured signal and the output from the generator filtered through the measurement matrix. When the optimization procedure terminates at Z star, the reconstruction for the measured signal Y is given by inputting Z star into the generator. Here we see the results of using the GAN reconstruction algorithm on images of flowers. The top row is the original image and the bottom row is the reconstruction from measurements, outputted by the generator of the GAN. Note that the reconstruction quality is limited by the ability of our generator. At the bottom we see sample outputs with random noise from the generator. We have reconstructed natural images. However, we are limited by the fact that our generator output is low resolution. As a next step, we plan to improve the reconstruction of natural LDR images and then extend to HDR images.
Thanks.